a private nonprofit research organization, has put together and started awarding in the context of this conference since its second iteration. So in 2011, we gave our first award out, and that went to Xi Shi, who worked with Conrad Wilner and Jürgen Oberst out at DLR. So this year we had a number of student paper entries. We had 9 student papers. They were actually all excellent. We had a hard time figuring out who the award should go to. So ultimately, the decision was made to award it to Tushar Mittal, who is a graduate student in his third year at UC Berkeley. And Tushar has the distinction of having had already a background in astrophysics and is currently doing his thesis work on magnetic systems on the Earth. So he's combined his interest in both astrophysics, astronomy, and also earth sciences to put together a really interesting paper on the geophysics and tidal evolution of Phobos. So I won't delay this further. Our award is essentially a small diploma, which you'll get in the mail, but also a $300 check that I have here. So after your talk, young man. After the talk. And again, congratulations, because you really did a fantastic job on this abstract. So it's based not on the posters or the presentations, based on the abstracts. Okay. Thank you.
So can people start the poster? Ask you to tell them.
You have to be working with it because they're
All right, thank you very much for this honor. All right, thank you very much for this honor, and I'm really glad to be able to present some of the work that I did on Phobos with my co-collaborator Ben Black, who's now at SUNY. And our focus of this work was slightly different from what we've seen at the conference up till now. So we've talked a lot about, we've seen multiple really nice talks about how Phobos formed, what's its current environment. And I'm going to slightly shift focus in trying to think about, what's going to happen to Phobos in the future. But I'll try and cycle back, because I think this question actually has implications to answer both of the questions that we're interested in terms of the formation of Phobos and its current state. And just a quick reminder, right, why is the evolution of Phobos interesting? So I would say, right, there are 2 main things that I was really motivated by for doing this work. Firstly, we've heard a lot about the impact hypothesis for Phobos, which generally ends up predicting that you should form either one large moon or multiple large moons besides Phobos. And they should evolve into Phobos and have some interesting dynamics. And the way I think about Phobos now, if we try and look at its future evolution, that would give us a test case of what could happen. And the second thing I would like to point out is that I think of Phobos as a test case for understanding the interiors of small bodies. And the nice thing with respect to Phobos is we understand some of the forces that it's experiencing. So it's like a really slow, long-term natural experiment that we have, and if we can understand some of the properties, that would inform us, essentially what are rubble piles, what are the material properties. And also, before moving forward, I would like to acknowledge that this particular problem is not a new one. A lot of people have worked on it and done really good work. What we're doing here is kind of synthesizing some of those pieces and adding a new aspect to it from some of the earth science models to relook at this problem and build up a comprehensive picture. So essentially, what we were looking at was 2 end members. So you can have 2 possible fates. One is that you have Phobos right now here, it keeps evolving inward, and it eventually hits Mars. That's sort of the standard case. The other possibility is that as Phobos evolves inward, it experiences more and more tidal stresses, it breaks up, and Mars might end up getting a ring, which would eventually decay and deorbit and hit this Martian surface. So the first part of this problem was to say what is the orbital evolution of Phobos. And this is the full sort of orbital evolution equation. What I would like you to focus on is a couple of pieces. So this is just saying what is the orbital evolution of Phobos as a function of time. This is the ratio of mass of Phobos divided by mass of Mars. And this is saying how it's dependent on the distance of Phobos with respect to the Martian radius. And just to clean it up a bit, you have two important pieces here. So first is that the orbital evolution is directly proportional to the mass of the satellite, and it's a very strong function of the radius. So if you start Phobos out close to the synchronous period, it takes a really long time for it to get to where it is. But as it gets closer in, it would evolve much faster. Also, if you had a much more massive satellite, it would evolve on a much shorter time scale compared to Phobos. So these are the results of calculations we did for the orbital evolution of Phobos, starting at its current location, which is about 2.8 Mars radius. And these are some of the physical parameters that go in terms of the tidal properties. And I've sort of taken a very conservative estimates. Most likely the reasonable values are more the decline. So what you find is that if Phobos were to continuously evolve, it would impact Mars in about 20 to 40 million years. So it's going to happen in a geologically recent time scale compared to how long it's been there. Now to get back to the question of the fate of Phobos, we now know we have some idea of, okay, this is the orbital evolution time scale. To ascertain what would happen to it, you need a force balance. So you can just do, let's say, what are the main forces that act on Phobos? So you have the tidal forces, which you can get if you know the orbital evolution to some extent. You have the centrifugal forces, because as it's going to move in, it's going to spin faster and faster, to say in the synchronous locking. It has some small self-gravity, which tries to hold it together. And then it has some cohesion. And what I would like to argue is that all these other pieces, there are uncertainties in the in the tidal parameters for Mars and so forth, but we still have some good understanding of all these three pieces. It's sort of this last piece of what is the cohesion of the object that really determines what's going to happen. And the way we approached this problem was slightly different to some of the approaches we've heard in this conference in the morning, especially by Terry Hufford. We said, okay, let's try and estimate an upper bound. So what we could do is we could say, let's take a volume average stress field on a rotating, self-gravitating ellipsoidal satellite. So what our calculations would give us is the upper bound on what the amount of critical strength you need to prevent breakup. In reality, some sections of Phobos might be weaker than what we calculated, so you might start to get landslides and so forth. But this would sort of give you a very conservative estimate of whether Phobos can survive hitting Mars, or would it break up into a ring. Okay. So there are multiple models people have used to estimate strengths of rock, and this is one of the sort of very popular model that people use a lot in the planetary science community, also in the earth science community. And effectively, all these terms are just the stresses you encounter as you move in, which you can calculate, which include the tidal stresses, the self-gravity, and the centrifugal. And what I would like you to point out is that there's one parameter here, which is defined as this, which includes the cohesion term. So what one could do is you can invert this equation so that you can say, okay, what is the cohesion that I would need in order to survive as I move in? That's the minimum amount of cohesion that I need. And the reason why this question of the cohesion is important is that the strength of objects is scale dependent. So we can go and measure samples in the rock, which people have done, and you get some estimate of the strength of objects. But what we see in earth sciences is that as a function of scale, things are much more weaker. And that's not quite surprising, because on large scales, if you look out, you would take a small piece of rock and do an experiment. it would be nice and clean and you could get some strength. But if you go on a macroscopic scale, things have fractures, things have gone through evolution. So they might be weaker than what you would expect. So one has to be careful in estimating what the strength you need in order to survive, because you need to account for some of the scale dependencies of properties. And what we're doing was to use a model that's been developed in the geotechnical community to estimate rock strengths, and it's called the Hoek-Brown rock strength model. So this is a semi-empirical model that's been developed using actual experiments, or you go to places where they have an explosion nearby and you measure the strength of rocks. And these are the types of models people use when you have to build a tunnel. You need to know how strong the material is. And you end up using models like this, and they have been calibrated. So we argue that this type of model makes a bit more sense when you're looking at macroscopic objects, rather than looking at the microscopic material properties of pristine samples. So what we did was, firstly, this is the distance from Mars. So you start up here and then you move in. The Drucker Prager criteria, one can calculate the amount of cohesion you would need in order not to break up. So this is the minimum amount of cohesion you need in order not to break up, and that's this blue envelope right here. And it's an envelope because you also have to assume something about the friction angle, so we choose a really conservative limit. So you get sort of an envelope instead of a single line. So what you find is that right now, Phobos, at least to break globally, doesn't require any cohesion strength. You have enough sort of self-gravity in order to keep it as is. But as it moves in, it would require some amount of cohesion in order to survive breaking up. Now, on the same plot, now I've plotted some estimates of what strength is, what this cohesion value is. And these two bands are from the Hoek and Brown model. And what I've distinguished into is breaks where you would expect, if it's very, very damaged, it's very fractured, this is the amount of cohesion you would expect. If it's not very damaged, then this is sort of the range of things you would expect. Just for comparison, I've also plotted the strength people have estimated for the Tagish Lake meteoroid. So that's a carbonaceous meteoroid that has spectrally a very good match to Phobos surface, at least. And since it was a fall, you can estimate when it broke up in the atmosphere, and that gives you some estimate of the strength of that material. One could also look at the estimate of the cohesion that you would have based on some estimates people have done for the rotational velocities in asteroids. And this is of the same order as the cohesion of regolith that has been talked about a few times. So if you were completely like a regolith, you would not have too much cohesion and you would break up quickly. If you had more of an intact rock, you might still break up, it would be much later. And furthermore, since we do have a big impact on Phobos, people have done numerical calculations which suggest that you would also produce a lot of fracturing and breakage during that impact process. So it's reasonable to expect that the actual material properties for most of Phobos would be more akin to a fractured rock rather than a solid intact rock. So one could take those results and then plot them in a slightly different space. So this is again the radius. This is the amount, and this is the friction angle now. And what this is basically showing is what is the region in space where the curves intersect. So this is where the blue curve and these bands intersect. So what you find is that for estimates of Phobos based on the Hoek-Brown model, Phobos should break up somewhere between 1.2 to 1.4 mass radius. If it was much more intact, then it might survive. One could also use the Hoek-Brown model to estimate the failure criteria, and that ends up predicting an even weaker estimate for where breakup would happen. So you would break up even earlier based on that model. So since the final result from a model was that you could have two end members, so you might break up or you might form a ring, and you might break up and form a ring or you might impact. We tried to do some simple calculations of saying what the ring evolution was. And I will not go into the details, it's in our paper, or you could talk to me later. But what you find is that if you start with a really narrow ring at about 1.2 mass radius and allow it to evolve, it takes about 1 million years before it starts hitting the Mars surface and the orbit. If you start it much farther out, you can have a ring that would survive for sort of tens or hundreds of million years. And at least initially, the density might be pretty high compared to some of the other ring systems we think about. One could also do a calculation to see if you do have chunks of Phobos that do not break up during the ring formation, what would it look on the surface? So this is just a calculation where we start at the top of the atmosphere for different size particles. They all start at the same location, and then they fall down. And because different size particles would experience this different drag, you would end up getting a distribution on the surface where the different impactors would not be at the same location. So this is some type of signature that one might expect even for a larger moon if it didn't break up completely. This is the type of features you might want to look at the surface to see whether that has happened in the past. So in the end, the final proposed evolution model we have for Phobos is it's going to evolve inward. It's mostly going to form a ring at some point in time. There might be small intact pieces of Phobos that might survive, that might hit Mars, but most likely it would very likely form a ring, at least part of it before that. And just to highlight a few things, right? So this model, the main parameter that we had to play around with was the strength of Phobos. And this is something that future missions can help improve and help constrain some of those model parameters. So for instance, there's been a lot of discussion about the gravity measurements, both from gravitymeter, radio science instruments, and so forth, which would tell us something about mass distribution. And one could then do a more detailed calculation instead of assuming just volume average stresses. Furthermore, improved constraints on the composition of Phobos would also help ascertain the material properties that goes into the inputs of these models. Thank you. Questions? Yeah. Yes, so the calculation I was showing you was I was saying that is when the edge of the disk, at least one of the edge of the disk would start hitting the Martian atmosphere. You're exactly right that there would be another edge of the disk which spreads out, and that can form subsequent moons. That's the calculation that we didn't include, but that's something that would be interesting to look at. Yes.
Great talk, really interesting.
Thank you.
I'm curious, given just the picture there, right? Mars has a lot of topography. It's got a lot of mass, the mass distribution is different. It's not homogeneous.
Yes.
Is the ring close enough to the surface that would see that? And would you see, some tilt in some particular direction or some warp over Tarsus or anything like that?
So the calculations we were doing, we didn't account for the full 3D gravitational field of Mars. There would be interesting things that would happen, and also the fact that Tarsus, if it's more recent, if you had a ring in very early on, that might have a slightly different distribution compared to what it is now. So that would be, again, an interesting thing to look at.
Okay, thank you.
Thank you.